Good morning, good afternoon, or good evening, depending upon where you are in the world, and welcome to today's webinar, Secure Robotics in Motion, a full stack approach using EtherCAT, brought to you by Tech Online, GigaDevice, and broadcast by AspenCore. I'm Colleen Heckman, and I'll be your moderator today. I have just a few brief announcements before we begin. First, the slides will advance automatically throughout the event. You may also download a copy of the slides by clicking on today's slide deck in your resource box located to the right of the presentation window. Today's presentation will be followed by a lively Q&A session, so we encourage you to ask questions throughout the webinar by typing your question into the Q&A text area located to the right of the presentation window and then hit the submit button. If you experience any technical problems during the webinar, just type your issue into that same Q&A text area, hit the submit button, and we'd be glad to offer you one-on-one assistance. And now, onto the presentation. Secure Robotics in Motion, a full stack approach using EtherCAT. Discussing today's topic is Kevin Jones, Business Development Manager at GigaDevice. Kevin has over 25 years of experience in the semiconductor industry, working as field application engineer, applications engineer, including specific topics like protocols for smart metering and smart energy, and later with business development specifically related to MCUs. He began his career at Hitachi Electronics Europe, and then further developed it at Toshiba Electronics and Renesas Electronics for 19 years. It's with great pleasure I now turn things over to Kevin to begin. Kevin, take it away.
Thank you very much, Colleen. And yes, good evening, everybody. Good morning, based on your time zone. So I'm located in the UK, so it's good evening for me. And thank you very much. Welcome to our webinar today. So as Colleen mentioned, it's a webinar entitled Secure Robotics in Motion, a full stack approach using EtherCAT. And as she's mentioned, so my name is Kevin Jones, and I am a business development manager in the MCU BU in GigaDevice, or at GigaDevice. So what will we talk about today? So for those people that aren't aware of GigaDevice and the company, I will give just a single page brief introduction to the company. Before we talk about the advantages of EtherCAT and some of the key features of EtherCAT, it's probably important for us to look at some of the challenges that we face within industrial automation and robotics. So we will touch briefly on those. That will then bring us nicely into the advantages of EtherCAT and why EtherCAT has been chosen as a technology. Functional safety. So we will then touch on functional safety and the security imperative. It's about protecting the robot's environment from any external hackers or external malicious connections. We will then touch on the robotic solutions that GigaDevice have. So again, we offer many different products, so we'll touch on those briefly. And then to wrap up, we will have introduced a section on continuing a journey. So after the webinar today, maybe there's some other interesting articles or where you might want to look if you're interested in EtherCAT or any of the applications. And then finally, we'll do a quick wrap up with a summary slide, and we'll go back to Colleen for hopefully some QA session. Okay, so I need to get used to that, to advance the slide, sorry. So an introduction to GigaDevice. So GigaDevice was formed in 2004. It was founded in Silicon Valley, and then actually formally located the headquarters in Beijing in 2005. So last year we officially celebrated our 20th year. And since then, the company has grown formidably, basically. I mean, it is now, as of last year, a $1.3 billion revenue company, and it's achieving quite significant growth. In 2025, when we achieved 25% year-on-year increase, and again, something that is quite formidable for a semiconductor company in this industry. It's averaged over the last 12 years, capital annual growth rate of around 22 to 23%. So something that's, quite formidable, and obviously a good choice from the founding partners. So as a company, we reinvest around somewhere between 15 and 20% of our revenue back into R&D. So the company itself is very, very much focused on product quality and product reliability. We have all sorts of longevity programs, etc., and we're committed to all the quality management, all the ISO certifications, etc., environmental management, occupational health and safety, etc. So yeah, the company is very, very committed to these things and innovation. So to give you an example, it was one of the first Chinese companies to introduce a ARM core to the Chinese market. It was also the first Chinese company to have an ARM total license or an ARM total access agreement, giving it a flexible licensing model with ARM IP and all the development tools that come with that. It is also one of the first companies to introduce, in fact, probably one of the first companies worldwide to introduce a RISC-based architecture back in 2019. So a first mainstream RISC-based processor. We have around 20,000 or over 20,000 customers with over 2,000 employees located worldwide. We first introduced an MCU in around 2013 and have since shipped around 2.5 billion MCUs. We're currently ranked number 2 for SPI NOR Flash globally and currently ranked number 7 for 32-bit general purpose MCUs, and currently ranked number 1 in China for 32-bit general purpose MCUs. And some of the major milestones recently, we recently listed on, as of last year, listed on the Hong Kong Stock Exchange, and also announced our overseas headquarters in Singapore. So as you can see, we are a very large semiconductor company. Oh, sorry, I will get used to advancing the slides. So the robotics challenge. The robotics challenge for me can be split into quite a few different subcategories. So for me, there are probably 8 different or 8 subcategories. So I've grouped the first 4 into the category of movement. So how the robot moves, and we'll look at those. And then the other 4 categories I've kind of lumped into kind of an other. So if we look at the first challenges, first ones are related to degrees of freedom. So when you talk about robotic systems, you'll hear the word degrees of freedom mentioned many, many times. So what does that mean? I have a little Toblerone bar here, and I'll hold it up in front of the screen, which just about works. So it is said that a solid, rigid object has 6 degrees of freedom. So what does that mean? So if I hold my Toblerone, apparently the rigid object is free to move in the X plane, as so. It's free to move in the Y plane, as so, and free to move in the Z plane. So there you can see 3 different degrees of freedom. It's also said that it can rotate. It can rotate on the X plane, it can rotate on the Y plane, and it can also rotate on the Z plane. So there you can see a solid object has 6 degrees of freedom. There is a reason for doing this with the Toblerone bar. I gave this or a very, very similar presentation a few months ago. Unfortunately, that was live, or I know this is live, but this was a face-to-face session. And to try and make the presentation more engaging, I actually offered the Toblerone to somebody who could answer my question towards the end. So in the hope of making this a little bit more engaging, I will ask a question towards the end of the presentation in the hope that maybe you pay more attention as we go through the webinar. Unfortunately, though, I cannot offer the Toblerone as a gift. Instead, I will just enjoy that with a cup of coffee a little bit to celebrate the end of the webinar. But anyway, the thought process there, I will ask a question at the end. I'm not expecting anybody to answer it, so please don't pop any messages in the chat. But hopefully it's to make it a little bit more engaging. So their degrees of freedom. If we look at our robotic arm here, we can see there's probably 1 rotational joint here. So there'll be 1 degree of freedom. Probably another rotational joint on this arm, another one here, probably 1, 2, or maybe 3 rotational joints here. So if we look at this robotic arm that we have on our screen, then there's probably somewhere between 6 or 7 different degrees of freedom in this robot. Probably important to point out that not all joints in a robot have only 1 degree of freedom. Some joints, like shoulder joints, have multiple degrees of freedom. But for today, let's keep it a little bit simpler. and just suggest here that each of these arms is only 1 degree of freedom. It can operate in one of the planes. So multi-axis synchronization, what does that mean? If we want our robotic arm or our robot to move in a linear line from, or let's say from point X, try and move my hands, from point X to point Y, then basically we are moving on the X plane, and we're also moving on the Y plane. So we moving between those points. But if we want to do that in a linear way, then what we need to do is we need to synchronize our movement on the X plane and our movement on the Y plane to allow this multi-axis synchronization. So that's what we mean by multi-axis synchronization. As you can see there, for things like pick and place machines, obviously we want very accurate movement and very coordinated movement to be able to position our robotic arm in the exact place in a 3D in a very precise time. So that's what we mean by multi-axis synchronization. Communication latency, again, if we're wanting our robot to move in a very, very synchronized way, then actually we need our communications control from the master unit to all of the robotic joints to happen in a very, very fast and, most important, a very deterministic way. So determinism is hopefully a word I will repeat many, many times throughout today's webinar. But that is one of the key features. It's the determinism. We need to be able to ensure that each of our joints is moving in a very, very synchronized and coordinated way. And this is one of the key challenges in the robotics system. So not only do we have lots of degrees of freedom, we have multi-axis synchronization, and we need a communications mechanism that can do that. Again, in industrial automation and in robotics, we're also dealing with a lot of complex motion mathematics. These are generally high speed, high precision, or high torque motors. So they require a lot of complex control and algorithms to be run to be able to control the speed and position of them. So again, these 4 challenges we have grouped together as, all related to the movement of our industrial automation system or our robotic arm. So the next group, kind of lumped them all together, but basically then we're talking about things like system reliability and safety. So again, that is how we protect the robot and the robot's environment from things that go wrong within the robot itself. Cybersecurity risks, again, something that's becoming more and more prevalent, but how we protect our robot from any malicious external factors. Space constraints, if we look at our robotic arm, you can see here there's a lot of cabling here. There's probably not so much room inside these joints. So again, in robotic systems and industrial automation, then these are very, very physical constrained environments. The PCBs themselves are generally manufactured with a specific form factor to fit within inside the joints, allowing the joints as well to move. So again, because they're physically enclosed within these joints as well, they can operate in very, very harsh environments. We can have very, very high temperatures, and we can also have very, very high electrical noise in big machine environments as well. So they are some of the challenges that we face. So then how do we address them? So before I do that, and maybe a little hint towards the question, but a typical humanoid dexterous hand has around 10 to 20 degrees of freedom. So as I say, we'll ask a question towards the end. That's a little bit of a hint. But yeah, just trying to make the webinar a little bit more engaging, a little bit more interactive. So the advantages of EtherCAT. So EtherCAT was invented in around 2003 by a company called Beckhoff Automation. At the time, there were plenty of other protocols and other systems that could have been used for industrial automation. But at that time, they were not considered as necessarily quite fitting to this, this application area. So for example, we had things like the CAN bus, we had Modbus TCP, we had Ethernet. So if we take CAN bus, for example, then the CAN bus at the time was limited to around 1 megabit per second and had a relatively restrictive payload of around 8 bytes. As you can see on the diagram, if you have lots of slave devices, so if you have lots of joints, then 8 bytes is considered, not enough information to portray or across our network to be able to control these systems. Also, with things like CAN, then the data rate, the 1 megabits per second, generally drops off as our cable distances increase and things like that. So when we had things like Modbus TCP and Ethernet, so again, Ethernet is probably a great technology. We have very, very high data rates, and we have very, very large payloads. But the problem with things like with technologies with TCP, if we consider, an Ethernet network with TCP, then generally it works on a client and server mechanism. So by that, we can have the client or the server instigating or creating messages within the network. So as they get transferred, then either we have to put up with collisions, and with collisions, we might have to have packet retransmissions, or we need to introduce some sort of time division on our media access, or we have to have some sort of carrier sense mechanism to allow fairness of transmitting these messages on the network. Obviously, one of the limitations of that is we want very, very deterministic and high-speed communications for robotics. And if we can't control when the frames go onto the network, then the determinism is somehow reduced. Also, with TCP sort of systems, then the processing, if you like, is done on the upper layer. So you might well have a source and destination address, and generally then we have repeaters and server devices. So as the frames are propagated through our Ethernet network, then it's up to the servers to then process each frame, probably in turn. It then needs to look up where the next hop in that network would be, and it needs to relay the frame on the network. So again, this processing just adds further delays, and it also means we can't control exactly the order in which the frames are being transferred in the network. So this was one of the key features for EtherCAT being developed. So one of the first advantages for EtherCAT is it uses the same physical layer and the same data link layer as Ethernet itself. So that means we can reuse the very, very fast bandwidth. We can also then have very, very large payload frames. But probably the biggest advantage is we can reuse a lot of the hardware that already exists for Ethernet. And that means we have a very, very cost-effective solution. Also works on a master-slave architecture. So there's only ever one device on the network which can transmit a frame, and that is the master. And each of the slaves are basically slave devices within the network. So I have a little graphic here which I will try and push as I continue to talk. Yeah, so that's going through. So as I said, this works on a single frame architecture. And what that means as well is that means every single node on the network, the slave device, has a particular area in that frame where it is receiving the information, and a particular area in that frame where it is going to populate its information in the frame. And the key point here is it does the processing on the fly. So that means the frame never actually stops within the network. The information is passed in each slave as the frame transfers through the network itself. So that is one of the fundamental advantages. Let me just pop back to the original slide. Yep. So again, it's a single frame. The information contained on that frame is for each slave device, and there's an element in each frame for the receiving and transmitting part on each slave device. So one of the key advantages here is there are no switches, and it generally works on a 2-port system. It does have more ports, but for today, let's make it a little bit easier. It also, and this is one of the highlights for EtherCAT, it works on a distributed clock system. So what that means is the master on the network inserts a timestamp into the frame as it traverses the network, and each slave device also does the same. It will insert a received timestamp into the frame. And you can see in the graphic, then the frame is actually transferred through all the slaves and back to the master. What that allows the master to do then is actually adjust the clocks in each device and also build up a good picture of the time distribution of the frames as they transfer. So it actually can coordinate and synchronize all of the slave devices on the network. That gives us in EtherCAT a cycle time of around 20 to 250 microseconds, and a jitter of less than 1 microsecond. So one good way to picture that, if you like, is a heartbeat. So the cycle time is our pulse rate, so that's how the heartbeat, how often the heart can beat. And the jitter is, if you like, the rhythm. So the jitter means we know from the master that the frame will be received at the slave at less than 1 microsecond variation. And it's the variation that is very, very key. That's what we call the jitter. So by adjusting these clocks, for having a very, very fast processing, we can achieve very, very deterministic communication at very, very high speeds and very low cycle times. So this is one of the key advantages of EtherCAT. Should point out as well that this company, IPC2U, I will mention them at the end, but the graphic obviously came from them. So the next area I'd like to highlight of EtherCAT, one of the advantages here is in the context of EtherCAT, FMMUs, for field bus memory management units, and sync managers are critical hardware entities within an EtherCAT slave controller, and they manage how the data is handled and synchronized within the network. Okay, so from the field bus memory management unit, it is responsible for mapping logical addresses to a physical address. And they allow the master then to view the entire network as one contiguous 4 GB logical address space. So as far as the master concerned, it just appears as one single memory map. Key features of this, it allows the on-the-fly processing. When the nodes are looking for the information for them and to them, it is always contained in a physical or linear address space, which means the processing is very, very fast. Processing times are typically within nanoseconds, so we're not adding any delay. Also allows hardware efficiency. So on the master side, the master is not continually having to translate messages for each logical node. It can do it in a single logical address space, and that means it reduces a lot of the processing power needed on the master devices themselves. The other key feature here is the sync manager entities. We haven't gone into the details, and unfortunately there's not enough time today, but there are different methods of using an EtherCAT slave controller. So we have different modes, but basically the key feature of a management entity is to ensure data consistency for the dual port RAM. So obviously we have an application layer, we have our physical layer, which is all trying to put messages onto the network and take messages off. So we need to ensure that they're not accessing this memory at the same point and protecting it from that point of view. So we have things like mailbox mode, we have buffered mode. Mailbox mode is kind of as that, then basically each device has to wait until the mailbox is full. It does that, and then it processes the information once the mailbox is completed. So it's used for things like acyclic communication, non-real-time information. We also have things like buffered mode. So basically then you have 3 buffers, and the slave or the master always has access to the very latest information on the network. So we can consider those as basically the ports at which the external field bus enters our EtherCAT. And just to give an example, a typical system would generally have around 2 or 3. So a typical EtherCAT slave would have around 2 or 3 FMMUs or sync managers. Now, the key point for EtherCAT is the number of external devices that a node can support. Okay, and this is key, and I'll come on to it a bit later, but the number of external devices a node can support is limited generally by the number of FMUs and the sync managers that are contained within the EtherCAT slave control. Okay, so they are some of the fundamentals of EtherCAT. How do we achieve that from a hardware point of view? So the easiest way for me to highlight that is to pick up one of the devices from GigaDevice, and that is the GD32H75E series. So you can see here, if I highlight, this device actually has an integrated EtherCAT controller with 2 Ethernet PHYs. It also comes with a genuine Beckhoff EtherCAT license. It also contains 8 FMMUs and 8 sync management entities. So it's capable of being an end node for other devices within the EtherCAT system. So how does that look? Maybe if I just touch on the CAN functionality. So this particular device has 3 CAN FDs. I mentioned that CAN wasn't necessarily a protocol of choice back in 2003 for industrial automation, but the CAN can be useful then to hang additional devices or additional nodes into the network. So the CAN full FD can then be used to maybe connect to other devices such as the GD F505, F503, or the GD 32G553. So they are all capable of complex motion control, so they can drive up to 2 complex motors as well, but hanging off the CAN FD rather than the EtherCAT. So if we consider a robotic hand, and if we consider the cabling, which is quite restrictive in a robotic environment, we might only be able to have one EtherCAT backplane, but we might want to control multiple joints or multiple motors within, let's say, for example, our hand. So what this device then would allow us to do is we can connect the EtherCAT PHY, we can drive at least 2 complex motors from the H75E series, but we can also connect other nodes such as fingers or joints via the CAN FD interface. So it allows us to connect other devices and hang them off the network. CAN FD can then also be used for things like actuators or sensor data, which is non-real-time critical information being transferred on the network. So these systems as well have typically very high processing power. So they're generally built on ARM Cortex-M7 cores. This particular device is running up to 600 megahertz. And as I mentioned, it can handle then all of the multi-axis vector control algorithms and drive up to 2 complex motors. Also comes with a whole host of dedicated RAN or peripherals. So for example, these are high resolution ADCs. So with the high resolution, what that allows us to do is with a high resolution, we can detect very, very minute changes in things like shaft or rotor positions. Again, very, very handy for things like pick and place machines where we need very, very accurate movement in our robotic system. A very, very high resolution ADC also offers better digitization. So we have a better digital representation of what is happening in the analog world. With high resolution ADCs as well, we can filter out a lot of the noise. As I mentioned in the beginning, we have very, very noisy environments, electrically noisy environments. So by having high resolution, then we can also filter out some of the additional noise. One of the key points generally in these systems as well is they have very, very high speed sampling. So what that means is we can detect the rate of change in our motor positions to a high degree. So we can detect things like overshoot, and we can also then use it to be able to detect very, very fast changes in things like torque or speed of our motors. And again, with very, very fast A to Ds, we can also do what's called oversampling and therefore filter out other external noise sources. So as you can see, these are not just microcontrollers, they are very, very complex systems. These also come with a whole host of timers. So as you can see here, we have 10, 16-bit general purpose timers, 32-bit timers, but we also have AD timers, so advanced timers, and these are capable then of doing the complex PWM with dead time insertion and things required for motor control. And as you can see, there's a whole range of timer peripherals. They also come with generally hardware accelerators. So this device in particular has a TMU, so it's a trigonometric maths unit, and that is capable of running a lot of the sine and cosine algorithms and arctan, and it takes in a lot of CPU resources or takes away a lot of the constraints, if you like, on the CPU to run these algorithms in hardware instead. We also have then an FAC, which is a filter arithmetic controller, and that's useful again for doing in hardware a lot of the complex mathematics for things like FIR and IAR filter control. This device again also has dedicated peripherals for driving motors. So we have a HPDF, high performance digital filter. So that's used for things like external digital filter modules or external sigma delta modulators. And we also then have AD out, which is again a dedicated hardware peripheral for use with external encoders. So these then produce the bit streams we require for driving and controlling our complex motors. You can also see then we have very, very large caches and tightly coupled memory. Because we are dealing with very, very sensitive motion control and robotics, we need to ensure that our execution and CPU doesn't store, and it's very, very tightly coupled. So meaning there's no stuttering or stalling in the instructions that we are running for these systems. Okay, so a little bit of a small break for me, and then hopefully an anecdotal video. I'm not sure if you can have an anecdotal video, but what we saw there was in a robotic arm. It simply picked up a plant pot. Unfortunately, in the movement of the plant pot, it's dropped it, and you see the plant pot has smashed. But as more and more human interaction, or as these robotic systems become, more and more involved in human life, then you can see that functional safety has a very, very critical role to play in these systems themselves. So that video there was generated by Apollo AI. Had a little bit of fun with some AI engine to generate that, and the original came from Adobe Express. Oh, phew, didn't think my video was moving. Yeah, so as I said, a lot of functional safety. We need to protect the robot and its environment from the robot itself. So how do we do that? Well, again, in hardware, most of these systems have a lot of hardware mechanisms built in. So we have things like power on reset. We have PDRs, low voltage detectors. We also then have memory protection units, and they generally then have integrated CRCs. So this one has 8 regions built in. We also then have watchdog timers. So we have some running off the independent watchdog timers and some running off system watchdog timers. So again, there's plenty of hardware mechanisms built in. But not just that, then for industrial systems, there is an international standard. So it's the IEC 61508. And it's the international standard for the functional safety of electronic and programmable electronic systems. So what that is a recognized set of standards, and therefore there is a recognized set of certifications that you can achieve. And these are things like failure mode analysis, failure effects, diagnostic analysis, and manufacturers can do all of this tests, if you like, to ensure that their products are meeting the standards required in today's systems. So this device has actually got the certificates from a company called TUV. So TUV Rhineland, generally in Germany, but they are a very, very well known and very, very well respected test house for this sort of certification. So we have all the certifications that we can then offer to the end customers. We also then provide a comprehensive set of test libraries. So we have test libraries then that operate to check the CPU is functioning correctly, same with the flash and the RAM. And all of these can be packaged then, and we provide all of the information to our customers. So we can provide things like examples, user guides, and how to achieve all the corresponding safety integrity levels that our customers may achieve. So we can provide all of that as a package. So the security imperative, again, security is becoming more and more prevalent in our society. So how do these systems protect? Well, again, this particular device has a lot of hardware security mechanisms built in. These are things like cryptographic accelerator units, so they can run in hardware a lot of the latest cryptographic encryption engines such as AES, TripleS, all with connections to the DMA as well. So again, we're offloading a lot of the resources required from the CPU itself. Comes with hash accelerator units as well. They support the latest SHA algorithms. So these are SH1 all the way to 256 and MD, etc. Also comes with eFuse. So an eFuse is basically a one-time programmable section of memory which can only be accessed by the CPU. And that is useful then for storing things like the encryption keys themselves or hashes of encryption keys that can be used later on. And so, as I said, they can't then be accessed from the outside world. So on top of that, what we can do is we can build some particular security features. So we can have things like secure boot. So secure boot means that when the device wakes up for the very first time, it will jump to what's classed as the immutable bootloader. So it will always go to this section of code. And again, it's a one-time programmable area of memory. What that is then responsible for is it can use the keys that are stored in the OTP to verify and check the authenticity and the integrity of our main application. So again, you can verify that the application has come from an authentic source, or you can check that the application has not been altered or tampered in any way. Same works, or it works in a similar way then for things like secure firmware update. We can verify the authenticity of the image as it's being transferred. We can also verify the integrity of new images that we receive. We can also then swap them in memory, and then the immutable bootloader can verify which section of code and which application to jump to and run. So they are fully CRA compliant systems. As I mentioned briefly, they are, we're operating at a very, very tight physical constraints. So these come in BGA 240 ball packages, very, very small, 14 by 14 millimeters. And again, I mentioned they integrate then 2.5 and the EtherCAT slave controller. And this device can run stably at 600 megahertz across then the full temperature range. So as you can see, they are very, very complex systems. So just to give me a little pause for a minute, but as I mentioned, I had a Toblerone bar there that I was giving away to the best answer, but maybe just a time for me to ask a question. We've talked about degrees of freedom at the very, very beginning. So how many degrees of freedom are there in this robot that we are seeing on the screen? I will just pause, so please don't post any messages on the chat. I'll just let you think about it for a few seconds. Okay, so we said that a typical dexterous hand has around 10 or 20 degrees of freedom. I know from some of what I'll point out as well is the robotic marathons. They sometimes have 3 to 6 degrees of freedom in a knee joint. So as you can see, there's probably, I don't know, 40 to 60 different degrees of freedom in the robot. So the point of the question was not really to give the answer of how many degrees of freedom exactly there are, but to highlight how complex these systems are, and then how key it is to have very, very fast and very, very deterministic communications to be able to control all of these robotic joints in a very, very synchronized and deterministic way. So again, this is one of the features and advantages of EtherCAT itself. So on the right-hand side here, you can see a list of devices that we have for robotic systems and industrial automation. We have a whole host of DRAM. We have a whole range and series of flash devices, which I'll mention. We also have a whole range of MCUs, which all, again, are capable of driving at least 2 complex motion or motor control. So just to touch on those, we also then have an EtherCAT sub-device controller. So this has 2-3 ports of the EtherCAT sub-device network, so the PHY interfaces. It also then supports 8 field bus memory management units and 8 sync management entities. So I mentioned those at the very beginning. Obviously, they are what normally limits the number of devices we can connect to the network. Also then works with a distributed clock system. with varying supply voltages. I mentioned at the very beginning as well that GigaDevice is the second largest supplier of SPI NOR flash globally. So as I mentioned, we are, as a company, very focused on our product quality and reliability. So we have lots of different flash technology products, all with 20-year data retention. We have very full density products as well. So the GD25 SPI NOR flash comes with 512K bits up to 2 gigabits densities. The SPI NAND flash, then has 512 megabits all the way up to 8 gigabits. So we're very well known for our flash technology. One device I'd like to highlight is our GD25UF ultra low power SPI NOR flash series. So this operates at 1.2 volts. So basically offers seamless power integration and removes the need for any external lever shifters or any complex power management. And again, most of these then, or some of these, are available in very small compact packages, the WLS CSP package. So again, they are ideal for devices or applications with extremely limited physical footprints, facilitating lightweight industrial designs. So applications, again, such as portable wearable devices, hearables, ASIC platforms, medical devices, and again, limited physical footprints being something in the robotic and industrial automation arena. We also offer a whole host of analog products as well. I'm not going to go into the details of them all, but we have 6 different product series here with over 700 different part numbers. So we can offer devices, things like DC-DC converters, LDOs. We offer motor control drivers and motor controllers. We also then offer a lot of systems for ADCs and voltage references, and a lot of sensors and temperature controllers. We also then offer a whole host of analog sensor portfolios, so we can do fingerprints, optical and capacitive fingerprints for different market areas. We also then have capacitive touch solutions. We also then have lots of other sensors like pressure sensors, temperature sensors, humidity sensors. We also have an additional business unit which covers the DRAM that I mentioned at the very beginning. We also have an automotive business unit. So I mentioned we pride ourselves on our product qualities. So we have automotive qualified MCUs, flash technologies, PMICs, etc. So again, if anybody's interested, then please feel free to go onto our website later. As you can see, we have a whole ecosystem of products around industrial automation and robotics. So finally, what next? Just before I come on to what next, it's probably useful to mention, it might seem as though we've highlighted the features of the H75E series, but I'm pleased to say that actually 2 months ago, the H75E series won Best in Show at Embedded World. So for those that aren't familiar, if you're based in the Americas, Embedded World is one of the world's leading international trade fairs. So there's probably around 1,200 exhibitors from around 40 plus countries, all showcasing the latest innovation. And this product won Best in Show for the category of microcontrollers, microprocessors, and IP, and that was awarded by Embedded Computing Design. So these are generally done on a 15-point rubric. So basically that means that they are tested for things like technical significance, so the level of technological advancement and breakthrough, the industry significance, so the potential impact the product has on the broader market, innovation, how unique the solution is compared to other existing product offerings. So again, the judges then all sit down and look at the different points, and then they can select up to 3 different winners in each category. And I'm pleased to say that GigaDevice won in the case of microcontrollers, microprocessors. So it really is a very good solution. And finally, just something maybe for continued learning. Just in case you want to go away and you want to know more about EtherCAT or maybe interested in some of these solutions themselves. So there's a link here to the EtherCAT page of GigaDevice. So here you can find things like data sheets, user manuals, some of the application notes. There is also then a good blog on EtherCAT solutions. So again, that's probably a 5 or 10 minute read. useful. We also have here a 20-page white paper on humanoid robotics and industrial automation. So that might be something you're interested. So as Colleen mentioned, you'll get the slide deck at the end. You can simply have a look through and see if these are interesting. Some additional material. So again, some of these sites are information I've picked on and used for this webinar. This one of particular interest, the IPC2U. So again, they've got some great articles on EtherCAT and how it works, so I recommend that. Again, those who want to watch videos, you have quite a lot of good videos if you search for EtherCAT on YouTube. So there's a what is EtherCAT here by Rail Pars. Again, only a 6 to 7 minute short video, but very, very interesting. There's also a video done by the EtherCAT Technology Group, EtherCAT in 20 minutes. So again, this is something that is worth highlighting. Something I didn't get to add on to the webinar today, but we made a press release yesterday. So the GD32H7 series was actually involved and used many times in the Lightning robot. So I'm not sure if anybody's seen the news, but the Lightning robot won the Beijing Robotics Marathon. And yeah, this H7 series is used multiple times, and it's used multiple times in the knee joint. And if we look at marathon systems, you know, we've talked about precision, high accuracy. If we consider a marathon for a robot, then there's a lot of undulating terrain. There's a lot of different impacts. So to be able to run these closed loop systems thousands of times without errors or stalling is quite a significant feat. And as you see, the H7 series was used in that. So feel free to Google at the end or use your internet searches to find out about the Beijing Marathon. And I think it also completed it in the fastest time on record. And it's also important to have a Google, because you can see then some of the robot systems that actually fell over. Just makes it show, you know, it is very, very difficult. And the whole point of EtherCAT is this very, very synchronized deterministic communication. So I do have a summary slide, but yeah, hopefully today I've highlighted some of the fundamentals of the robotics challenges, the fundamentals of EtherCAT, the key feature being determinism. Yeah, and the GigaDevice has a comprehensive set of solutions for industrial automation and robotics. So I won't dwell on this at the moment. So I hope the webinar has been very, very useful. I hope it's been interesting. And I will hand back to Colleen for maybe a short QA session.
Yes, thank you so much, Kevin. That was a really great presentation. To our audience, I did want to point out some of those resources that Kevin just mentioned are in your resource box. So they're conveniently located there, but they're, of course, in your PDF download as well. So what we're going to do now is go to our Q&A session. If you haven't done so already, we do want to encourage you to ask questions. We will get to as many as we can in the time that we do have left. If we don't get to your individual question, someone will get back to you after the program is over. So Kevin, I hope you can take a breath there for a second, but we do have several questions that have come in, so I will go ahead and get started. The first one asks, what are the practical limitations or the deployment challenges of EtherCAT that engineers should be aware of?
Oh, hi. Excellent question. Thanks, Colleen. And I will add a caveat before I answer that. I'm not a designer of these systems myself, but I mean, I think from the presentation as well, you can see, I mean, topology is one of them. We've mentioned how the EtherCAT frames are transversed on the network. But one point to mention is, for example, if you have a robotic arm, you might have an EtherCAT system that is transferring all the way through the arm. And generally, this works on a system where maybe the master needs information from each slave. And if you have maybe a line break, then generally we could lose all of the communications from that line. So what the designers must then consider is what the topology would be. So is it better to have cable redundancy, maybe a loopback in the EtherCAT controller? But again, with loopback, then that means we are more physically constrained because we have to have, you know, two ways transfer of data. Yeah, these are, again, you generally would have to have some sort of EtherCAT compatible hardware. So a lot of the sourcing information needs to be thought of at development times, such as BOM cost informations. And again, you need to consider things like vendor maturity. You know, not all vendors offer the same level maturity level in an EtherCAT system. You need to consider things like configuration and diagnostics. So these are very, very complicated systems, and you generally then have complicated tools for a lot of the configuration. And again, for diagnostics, then you have a lot of complicated tools for a lot of the the analytics, if you like, the analysis of doing them. And you have to have a good understanding of these systems themselves. We've talked about the determinism of EtherCAT. So one point to mention is what happens when you have a non-real-time system. How do these systems then interact with the outside world? Most of our autonomous systems in a industrial environment would run off Ethernet. So how do we bridge that gap between an EtherCAT system and an Ethernet system? But something as well I've mentioned today is probably on certification and safety. So again, a lot of these systems have things like functional safety over Ethernet. So again, you need to consider which vendors you're looking at and which level of security and functional safety they are offering. So, I mean, as I said, I'm not a designer, but there is a whole host of issues to address.
Thank you. Sounds like a lot. So for the next question, this person actually is looking for an evaluation board, for the GD3H753. And how do I get a hold of one?
Yeah, that's a very good question. I'm kind of kicking myself a little bit. We had that on, I think, was it Tuesday? So yeah, if you're based in Europe and you're listening online, then we have a shop, gigadevice.eu, so please go on there. We have a whole host of distribution partners and sales reps as well. So you should be able to find the products online. If not, then feel free to reach out to me. Be interesting to follow up. If you're based in the Americas regions, then again, we have a whole host of distribution partners and reps. We do have stock of these boards in Europe and in the US or the Americas regions. So all I'd say is, you should be able to find them with our distribution partners. Check the gigadevice.eu if you're in Europe. Failing that, feel free to come to me or any of the sales representatives you are aware of for GigaDevice. And GigaDevice actually has on its website, if you look, then it will list all of the representatives and all of the sales offices in the Americas and in Europe.
Okay, excellent. Thank you very much. Okay, moving along to the next question. Again, if we don't get to your individual questions, someone will get back to you, but I think we can get through a couple more here. So this person mentions that you do talk about the advantages of EtherCAT, but what about other technologies such as ProfitNet, RT and IRT?
Yeah, again, a very, very good question. As GigaDevice is one of our focus markets into industrial automation and robotics. Presentation here, even though we presented on EtherCAT, we are not suggesting one flavor of technology over the other. So they all have different advantages depending on the application. So it's generally up to our customers to select which one is preferred, and we would support, looking forwards, we'll support all of the technologies. But ProfitNet RT, so real time, generally it's a software-based system. So it lets real-time traffic take priority, but it does still suffer the risk of high jitter, and the cycle times are maybe not quite as high as EtherCAT. One advantage though, it does then allow the use of standard Ethernet controllers and Ethernet switches. ProfitNet IRT, so an asynchronous version of ProfitNet RT, this then deals with some of the issues, if you like, of the delay. So it offers real hardware, real-time control. So this is fantastic for things like determinism. So again, you can achieve pretty much the same cycle times as you can with EtherCAT, maybe even quicker or even faster cycle times than EtherCAT. But the problem there with IRT is generally you require dedicated ProfitNet IRT capable switches, and they're hardware-based systems as well. So yeah, they are very, very different. And I would say as a designer, they should very much understand the advantages of each one before selecting the technology.
Okay, excellent. Thank you. We are going to fit in a couple more questions here for you before we let you go, and enjoy your Toblerone. Can I use, this one asks, can I use the Ethernet PHY on the GD32H75E device without using EtherCAT, or just as an EtherCAT PHY?
So no, you can't. I mean, one of the advantages of EtherCAT is, this determinism and this very, very fast processing. And to do that, it's necessary to do things in hardware. So it is a dedicated EtherCAT controller, and as such, then you can't connect Ethernet frames or process Ethernet frames.
Okay, and I'm going to quickly go through two more. If we use the standalone EtherCAT device, the GDSCN832, what interfaces can I use?
Okay, yeah, very good question. Sorry, I probably skipped over it a bit quickly in my slides. So I'm just going to push out slide there. Sorry, I'm going to move it onto my main stage so I can use the pointer. So highlighting here the interfaces that we can use. So as it says, it supports 8 and 16-bit serial and parallel communication. We support SPI, QSPI, octal SPI, and with EXMC synchronous mode. So yeah, these are the different interfaces you can use with the device.
Excellent.
To the outside world.
All right. Very good. I got one more for you. Do you have any plans to support TSN on this device family?
Oh, again, very good question. TSN. So what is TSN? TSN stands for time-sensitive networking, I think. So basically, this is a set of standards which are developed on top of the IEEE 802.1, so the Ethernet substandard. And they're all then developed to overcome this problem that we have in Ethernet. So to address the problem of determinism and synchronization. So again, why EtherCAT was developed in the first place. One of my colleagues mentioned actually, and a good way to look at this is like a highway. The highway works very, very well until there's some sort of congestion. So what these time-sensitive networks do is then they allow a single channel for things like emergency services. So even when the highway is congested, there is a dedicated line or a dedicated road, if you like, for the emergency systems to use. Problem with these systems is they're generally then quite complex to configure. As I say, they're built then above the Ethernet sublayer, and they generally require quite costly hardware. So at the moment, no, we have no plans to support TSN.
All right. Well, Kevin, thank you. That does look like all the time we have for questions. If we didn't get to your individual questions, someone will get back to you after the program is over. So for more information related to today's webinar, please visit any of those resource links that I mentioned in your resource box. Within the next 24 hours, you will receive a personalized follow-up email with details and a link to today's presentation on demand. So thank you for attending today's webinar, Secure Robotics in Motion, a full stack approach using EtherCAT, brought to you by Tech Online and GigaDevice. This webinar is copyright 2026 by AspenCore. The presentation materials are owned by or copyright by GigaDevice, and the individual speaker is solely responsible for his content and opinion. So on behalf of our guests, GigaDevice, I'm Colleen Heckman. Thank you for your time, and we hope you have a great day.